Lighting calculations. Okay, so in this problem we simply have a big set of values here, and we just need to identify how we're going to use each one, set up the geometrical representations of the vectors and the relations between them, build the factors that we need to multiply the colors with, and then identify which colors are which. So we're going to set up the diffuse part with Lambert, the specular part with Fong, and then add the ambient. And well, in this case we don't have emission, but we'd add that on afterwards, and so on and so forth. So let's begin by identifying sort of what objects we need here. So if we imagine we have just a point here, the position, let's call it P for now. At some point we have a light, we have an eye or a camera somewhere else. So P has a normal, which we can call M in this case, doesn't matter though. The kind of actual directions of these vectors don't matter in this case. In this image, we're just kind of identifying what objects we are going to need to calculate. So here we have the vector from P to the light, which we call S. We have a vector from P to the camera, which we call V. We have the direction to the light, the direction to the camera, and the direction of the normal, or where we're facing. And so we need values for these. So S is simply the light position minus P. V here, V equals the eye, or the camera's position, minus P. So to begin with, we'll simply need the values for those. So in this case we have P itself, the position, here, 1, 4, 3. We have the eye, and we have the light position here. If we go back here and say, well, just write this in here. S equals, so the light position is 3, 8 minus 2, 8 minus 2 minus P, which is 1, 4, 3. Which will give us 2, 4, minus 5 for S. V equals, so we have the I, minus 1, minus 1, 5, minus 1, 4, 3, which equals, so minus 1, minus 1, that's minus 2, minus 5, 2. Okay, so here we have the vectors S and V, and eventually we will have to find the halfway vector as well. Okay, I don't want these to be capital letters here. Halfway vector H is an approximation of a vector halfway between V and S, imagining a vector that would reflect S into V. And the halfway vector is simply S plus V equals 2, 4, minus 5 plus minus 2, minus 5, 2, which equals 0. 4 plus minus 5 is minus 1. minus 5 plus 2 times 3. Okay, and we can also write in here our normal n, which equals 0, 0, minus 1. Okay, so just looking at these normals, the idea behind the halfway vector is that it's the vector that would reflect s into v, and then we check the angle between h and n, and we can see that the vector 0, minus 1, minus 3 is not far from having the same direction as 0, 0, minus 1, so we're probably going to get a fairly strong specularity, although not full 1, and we can see the angle between s and n, which is also a little bit further away, but probably we will get some effect on that as well. So okay, here we have the vectors. Here we have the vectors that we need to continue with this example. So the next thing we need to do is the factors that we're interested in, because we're not really going to calculate this with these vectors here. We need to use those to get the factors that are the intensity factors for the diffuse part and for the specular part. And the diffuse part is simply this angle here. So we're going to be looking at the cosine of the angle between the normal and the direction to the light. So this angle here and the cosine between angles is simply the dot product of the vectors divided by their lengths, or the dot product of the normalized vectors. So what we're going to calculate here is now the factor Lambert equals I don't know if it's simpler for us to simply write this out here or draw this. So what we're going to get here is Lambert equals m dot s divided by the length of m times the length of s. In fact, what Lambert does equal is the max of 0 and this, meaning that if we get a negative number from this part, it'll become 0, but we're mainly interested in this part here. So what we're going to need here though is we're going to need the length of s, which equals the square root of 2 squared plus 4 squared plus 5 squared. So the length of s is the square root of 45. We'll just leave it at that for now. Okay, so Lambert now equals, so this should be m in this case, that's the letter we're using. So m dot s will be 0 times 2 plus 0 times 4 plus minus 1 times minus 5. So if we go back in drawing mode here, that gives us basically 0 plus 0 plus minus 1 times minus 5 is 5, divided by the length of m. And we can see that m is 0, 0, minus 1. So the length of m is 1 times the length of s, which is the square root of 45, divided by the square root of 45. So we have here that Lambert equals 5 divided by the square root of 45. And again, we'll just leave it at that for now. So this is our Lambert factor here. The other factor that we need, so this is the diffuse part of the light, the diffuse intensity. So another intensity that we need is the specular part, and the halfway vector that we calculated here, we are going to need to, so we're imagining a vector here, the vector h, that's halfway between the vector v and the vector s, and its length doesn't matter because we're going to divide by it anyway. And then we're going to look at the angle between h and m, saying that if h and m are exactly parallel, then m is between v and s, meaning that it would reflect the light directly between them. So specularity light is the light that reflects from the light into the camera, or reflects from the light and is reflected by the vector n here, the normal. In this case, like I draw this image, it would end up somewhere here, meaning that it's fairly close to being parallel to h, fairly close to being reflected straight in here. So this point would not get full specularity, but it would get pretty strong specularity. So what we get here is, let's do the same for the vector Fong, which equals, again, the vector h, the vector m dot the vector h divided by the length of m times the length of h. And again, it's really the max of 0 and this, but again, this is what we're interested in. So if we again look at this dot product here, it's 0 times 0 plus 0 times minus 1 plus minus 1 times minus 3. And we have 3 divided by the length of m is 1, the length of h we haven't calculated yet. So let's move a little bit to the side here and calculate the length of h. The length of h equals square root of 0 plus 1 plus 9, that's the square root of 10. So there we have the length of h, square root of 10. So and there's our Fong, or our specular intensity. And what we need to do now is simply to say, okay, we've used all these geometrical objects here to calculate, and we end up with the diffuse factor Lambert and the specular factor Fong. And continuing onwards in actually finding the color, that's the only thing we need. That's what we calculate from the geometrical objects, and so we can leave the vectors and such alone now and simply set up our formula here. So what we're going to need here, so we're asked about the color value, and we're going to need to really calculate the color values independently, the red, the green, and the blue. Inside our shader, we'd simply take the vectors and multiply them together. But here we're going to need to find each value independently. So let's start with the red value. So what we're going to do in each case is, let's start with ambience. So we have material ambience here, and we have a color of the light. So we'll just use the color of the light for all of these. So 0.3 is the red value of the light. Then we have diffuse and specular. Oh, sorry. Yeah, 0.3 here. So we'll say the intensity of the color in the end equals the ambient intensity of red times the red intensity of the light times the ambient intensity of the color. if we had separate values for the ambient part of the light and the diffuse part of the light and the specular part of the light, we'd use them respectively. But right now we just use the light color for all of them. So the ambient part will be the light ambience, no, the light color, times the ambient part of the material. The diffuse part will be the light color again, times the diffuse of the material, which is 0.6. So we'll add that to here, plus 0.3, which is again the light color. So we have the red color of the light times the red part of the material diffuse. So light times diffuse times Lambert, which is 5 by the square root of 45, plus the light color again, which is 0.3, times the specular part, which is 1, so we have 0.3. We can see now that when we just have the single light color, we could also take that kind of outside the parentheses and calculate the rest first and then the light color into it afterwards. Let's just stick to the plan here and use this for all of them. 0.3 times 1, which is the specular factor, times times 1 times, now we have the Fong, and that to the power of shininess. And shininess is 10 here, so this to the power of 10. So this is going to be the intensity of the red color. So we can also add that in here and say intensity for red. The intensity for red is just all these red parts. So we have red part of the light times the red ambience of the material, red part of the light times the red diffuse times Lambert, red part of the light times the red part of specularity times Fong to the power of shininess. So now I simply just have to calculate this and end with an answer here. And then we have to do the same thing for green and blue. So this equals just about 0.4, 0.4, so that'll be a red intensity, and just do the same for green. That'll be, and now I have to look here and see, okay, the light color for green is 0.7, so 0.7 times the ambience is 0.1, 1 plus 0.7 times 0.2 times 5 by the square root of 45 plus 0.7 times 1, 7 times 1 times 3 divided by the square root of 10 to the power of 10 equals, and finally the blue part here will be, we have 0.6 as the light color, we have 0.2 in the ambience, 0.6 light color, 0.4 diffuse times Lambert, always the same, dependent of the color, plus 0.6 times 1 times 3 divided by square root of 10 to the power of 10. So this equals just around 0.588, and this one just about 0.653, sort of, but in the end it's not the end values that matters, but the method of getting to them and understanding what's going on here. But in the end, we can now say that our red, green, blue color here our color equals 0.4, 0.588, and 0.653, and that's our final answer.